Good evening, Akshat. So this is aircraft propulsion course. My name is Aditya Sharma. This is aircraft propulsion course being conducted by Department of Mechanical Engineering, IIT Guwahati, under the NPTEL program. And we are into the fourth week of this very course. And the theme of this week's content is gas turbine attachments. So topics revolving that have been covered in this week's content. So topics like yes, good evening. So topics like reheater, yes, heat exchanger, and then intercooler. So these topics have been covered, and then numericals based on these topics uh, have been worked out, right? And how these attachments change the Brayton cycle, alter the Brayton cycle. So all this has been discussed in this week's content, week 4. I hope I am audible. My slide is visible. If not, you can point it out anytime in the session. Okay, so gas turbine attachments. So instructor for the course is Professor Vinay Kulkarni. He is affiliated to Department of Mechanical Engineering only, and I also am a research scholar here at IIT Guwahati. Okay, so the session will proceed in this fashion, the same way we have been doing in the previous sessions. So first, briefly the topics that have been covered in a particular lecture, and then questions related to that. So three lectures are there in this week's content: lecture 10, 11, and 12. Lecture 10 caters to the discussion related to heat exchanger and reheater, and lecture 11 is on your intercooler. And if all the attachments are attached to your gas turbine cycle, in that case, how the Brayton cycle behaves or looks like. So this has been discussed in lecture 11. Then problems based on these two topics that have been discussed in lecture 10 and 11. So this is the content related to your this week's content, that is gas turbine attachments, right? So we'll start with lecture 10. Okay, then let's see first the topics of lecture 10. So this is Brayton cycle with heat exchanger and reheater. First topic here is Brayton cycle with heat exchanger. Its schematic and thermodynamic cycle has been drawn. Then effectiveness of heat exchanger has been discussed, and what is an ideal heat exchanger cycle. So this has been discussed. Then next topic is heat and work interactions in the presence of heat exchanger. So this has been discussed. Then Brayton cycle with reheating. So up to this point, we were discussing, up to 10.3, we were discussing our heat exchanger. From 10.4, uh, we have discussion on reheater. Then here also schematic and thermodynamic cycle of a reheat cycle has been mentioned and discussed. Then heat and work interactions related to a reheater. Then how can we find out the optimum reheat pressure? So this has been worked out, and then the efficiency of reheater has been discussed. So briefly, let's see these topics. And then we will see questions based on lecture number 10. And after that, numericals I have kept in with the lecture 11 and 12's content. So, Brayton cycle with heat exchanger. I'll draw the thermodynamic cycle. Basically, is the TS diagram. Based on your TS diagram, you can do the whole discussion. So TS diagrams are very important when we need to understand gas turbine cycle. Okay, this is your compressor, this is your heat exchanger, this is your combustion chamber, this is your turbine. Right, this is again heat exchanger. So what we are doing here in heat exchanger is the air that is compressed and comes out from the exit of your compressor at point 2, if you see, state 2, if you see, we are exchanging heat with this air. All right. And what basically it does is that it changes the state of your working fluid from state 2 to state 3. Right? And now what are the repercussions of this step that we have taken is that the heat Q in that we are giving, right, to this cycle. So the temperature at which this heat is given increases, right? It increases from T2 to T3. So eventually what this will do is this will increase the efficiency of the thermal efficiency of the whole cycle, right? And if you talk about the work, net work, so does it do anything to your network when we talk about the heat exchanger? So the answer is no. All right. So it only helps in increasing the thermal efficiency of your whole system. So this basically is your heat exchanger in short. Then efficiency of heat exchanger has been discussed. Okay. effectiveness of heat exchanger has been discussed, and then one thing that we can notice, so in your heat exchanger, if you talk about ideal heat exchanger, if you talk about ideal heat exchanger, so these two takeaways are there. First is T3 is equal to T5. Second is T6 equals to T2. All right. So this temperature and this temperature, this temperature and this temperature. So these are equal in case your heat exchange is ideal. Okay. And from your this heat and work interactions, in the presence of from here, if you see efficiency, so efficiency basically is W net by the heat that we are giving. W net is work done by turbine minus work done by compressor divided by Qn. So if you see turbine work, this is H4 minus H5, enthalpy of at state H4 minus enthalpy at state 5. So this is your turbine work, right? And then for a compressor, this is H2 minus H1. So why we subtract compressor work from turbine work? I hope that is, there's no doubt in it. Then if you see the Q in, so Q in here we take the enthalpy at 4 minus enthalpy at 3. If you don't take it, enthalpy of 4 minus enthalpy of 2. Okay. So here the whole difference comes into picture. This denominator has decreased. Okay. Which eventually leads to increase in the thermal efficiency. So this is your from heat and work interactions. So this is one main point. All right. So this is about your heat exchanger. Up to point this. So this I discussed. This I discussed. Then is your Brayton cycle with reheating. So let's first draw the ES diagram. First we draw the thermodynamic cycle. If you can remember the thermodynamic cycle of a particular cycle, so that is a great positive in your favor. Okay, things become very easy. So this is for your reheater. So now what happens in your reheater? This is your compressor, combustion chamber, reheater, high pressure turbine, low pressure turbine. So we split the expansion of the products of your combustion, that is coming out of combustion chamber, into two turbines. One is with expansion from 3 to 4, other is with expansion from 5 to 6. And in this process, what we essentially are doing, or what we essentially do, is we increase the work output from the expansion of these gases coming out of combustion chamber. Okay. And is it how is it happening? So if you see the expansion, T3 minus T4 is for your high pressure turbine, right? For low pressure turbine, if you see, expansion is from, or you can write it H5 minus H6. This is low pressure turbine. Then, if such arrangement had not been there, okay, if only single turbine had been there, for single turbine, what would have been the WT, work output from turbine? It would have been H3 minus H4 dash. Now the point is A, B, C. So A plus B is greater than your C. So this is the whole point of using your reheater. Right? So in this process, though your work output has increased, but you have done this compromise with increase in your thermal efficiency, right? So these two things now you have to keep in mind and do the adjustments. So if you want to go for increase in work output, how much your thermal efficiency will suffer. So these things you need to handle. Okay. So this is about your reheater. Okay. And condition for your optimum reheating is the T4. This is your condition for optimum reheating, right? T4 is equal to T6. So this temperature at the exit, first these are equal. Second is these are equal to root of T3 into T1. T3 is this temperature, T1 is this temperature. Okay. So this is it about your reheater. Then moving on to questions. So there are diagrams also that say that how with your beta, that is with beta, that is your T max by T minimum. So with change in beta value, how your efficiency behaves or how your specific work output behaves. Okay, so I was discussing reheating and reheater. So I have mentioned the optimum reheating condition. Okay, and then what I was telling is that with your beta, that is T max by T minimum in your Brayton cycle, how your efficiency, thermal efficiency behaves, and how your specific work output behaves. So these things have been discussed in your lecture. But before that, we will look at the questions first, and at the end of the session, if we have time, we can devote that on discussion on these graphs related to beta. Okay, so I have discussed topics that are there in lecture 10. So then we'll move on to questions. So I have question number 1 here, which says that which of the following is true while incorporating a reheater in a gas turbine plant? So four options have been given. So you can go through the options and try to answer which one is the correct option. Four options have been given. First option is reheater increases the work output. Second is it decreases the pressure ratio. Third is it increases the compressor work. Fourth is it increases the pressure ratio. So out of these four, if you see the reheaters diagram, so this is your thermodynamic cycle for your reheater in a gas turbine cycle or Brayton cycle. So is your reheater somehow altering the work input to compressor? The diagram doesn't tell this. But if you see the work output, that is from your turbine. So is it altering the work output in some way? The answer is yes. So we have discussed this. Okay. A plus B is greater than C. Right? And is there any effect of reheater on your pressure ratio? So as per our discussion, there is no mention of a relation between pressure ratio and then your reheating, right? So in that case, out of these four options, which comes out to be the best option? Option number A, right? So we can choose this option as the correct option. This was question number one. I hope there is no doubt in this. And if so, you can just ask in the comment box. Okay. Then moving on to next question. Please read this question number two and then try to answer this. The question is on heat exchanger. So the question asks, the main purpose of heat exchanger in a gas turbine power plant is to dash is to increase the network output, to increase the heat rejection, to reduce the compressor work, to increase the thermal efficiency. So let's go to the diagram of your heat exchanger. So this is your heat exchanger. Then if you see the thermal efficiency in the heat and work interactions heading, under this heading if you see, so we have discussed this, that your denominator, what happens to your denominator? It decreases as we use a heat exchanger, and this eventually increases your thermal efficiency. So this is the main purpose of using a heat exchanger in a gas turbine cycle or Brayton cycle. Right? So heat from your combustion products, your working fluid or air from the exit of compressor is heated, which eventually increases the thermal efficiency of the whole Brayton cycle. So out of the four options, if you see option number D, so it increases the thermal efficiency. Your heat exchanger increases the thermal efficiency. All right. So these are two questions based on your lecture number 10. Then there are numericals based on your lecture number 10 that you will take along with numericals of lecture number 11 and 12. Essentially lecture number 11. Okay. So Brayton cycle, lecture number 11 is Brayton cycle with intercooler. And if Brayton cycle is taken with all the attachments, namely your reheater, your heat exchanger, and your intercooler. So topics are Brayton cycle with intercooler. So you have first of all you have schematic, then you have thermodynamic cycle, then heat and work interactions, then optimum intercooling pressure, then you have efficiency with intercooler, then you have Brayton cycle with all the attachments, and the schematic for that has been given, and the thermodynamic cycle related to it. So let's see Brayton cycle with intercooler first. So number 11. So let's draw its thermodynamic cycle. Using TS diagram. So this is your first compressor, this is your second compressor, this is your combustion chamber, this is your turbine, this is your expansion, so this is your low pressure compressor, this is your high pressure compressor, this is your combustion chamber, this is your turbine. Okay. Then So this is your intercooler. Okay. And what is the purpose of using intercooler? The purpose is that with the help of intercooler, the work input that is required to compress your working fluid or air, that decreases. Okay. So this is uh, fundamentally the work of your intercooler. Okay. Then if you see the optimum intercooling pressure, so the condition for that is T1 into T2 is equal to T. So this is condition where T1 is T2 by T1 and T2 is T4 by T3. So temperature ratios for both the compressors, high pressure compressor and low pressure compressor, right? Now also from here, from this point, you can deduce this. Okay. And why so? Because your T1 is equal to T2. So this is for your optimum intercooling pressure. All right. And this basically is T4 by P1 or P4 by P1 gamma minus 1 by gamma. So this has been worked out in your lecture number 11. Then is your efficiency with intercooler. So how your efficiency is dependent on beta. right? So at the end of the session, if we have time, we can discuss this. And also your Brayton cycle with all the attachments, because under this heading, essentially you have the behavior of your efficiency with respect to your beta. Okay, so we will see if we are able to cover this or discuss this. But before that, we will see the questions. So let's see the questions then. So first question I have, this is not a numerical question. After this question, all the questions I have for this session are numerical in nature. So please read this question and try to answer this. So I'm incorporating both your intercooling and reheating in a two-stage gas turbine plant. So if you see the options, so this option has commented on your thermal efficiency and work ratio. So what is your work ratio? W net by WT. So this is a work ratio. So your turbine work increases, right? Compressor work decreases. So work ratio improves. Okay, that is the point of using these two. Then what happens to thermal efficiency? So I've discussed in your when I was discussing reheater that your thermal efficiency decreases. Okay, with your reheaters. So in that case, the correct option comes out to be option number B. Okay, so B is the correct answer to this question. All right, then we have numerical questions. So this is first set of questions, first group. Please read this question first. What is given to us? First, we will write that down. After that, we will take the questions based on this paragraph or given data. So let's read this question first. An open cycle constant pressure gas turbine plant consists of two compressors with perfect intercooling and a two-stage turbine with reheating. So this is an example of gas turbine cycle with your intercooler and your reheater. Okay. So air enters at 1 bar and 28 degrees Celsius. Maximum pressure ratio and the maximum temperature of the cycle are limited to 5.4 and 790 degrees Celsius respectively. So pressure ratios have been given this. So 5.4 is for cycle, and maximum temperature at the exit of your combustion chamber is 790 degrees Celsius. Isentropic efficiency of each compressor. So two compressors are there and each turbine is 82%. For maximum expansion work, answer the following questions. Okay. Question number 4 to 8. Number 8. So let's draw the diagram first. Diagram is very important. So if we can draw a diagram, I would say 80% of the question is solved. Okay. So two compressors are there. So let's say this is first compressor. Then this is second compressor. This is 1, 2 dash. The real scenario is this. 2 dash is the isentropic scenario. 4 dash is the isentropic scenario. 6 dash is the isentropic scenario. This is for your combustion chamber. This is for your reheater. This is for your intercooler. This is compressor 2. This is compressor 1. Turbine 1, turbine 2. So this is your TS diagram for question number 4 to 8. Then what is given to us? At the inlet of compressor, that is point 1, you have 1 bar pressure. Temperature is 28 degrees Celsius. That is 301 Kelvin. Then you have pressure ratio as 5.4. Then maximum temperature at the exit of combustion chamber is this 1063 Kelvin. For your compressor, efficiency is 0.82 for both the compressors, for each compressor, and for turbine also 0.82. So this has been given to us. Then let's see the questions. First is total work consumed by the compressors. For both the compressors, question number 4 solution. First of all, we'll find out the pressure ratio across a single compressor. That how we can do by taking the square root. Because for the two compressors as a single unit, the pressure ratio has been given for the whole cycle. So if we take the square root, so this will come out to be this. Okay. Now in the question it has been given to us for perfect intercooling. What has been given? T1 has been given equal to T3. Because perfect intercooling has been mentioned, and perfect intercooling basically means that your this point and this point they'll be at same level. So I have not been able to draw it at same level, but these two will be at same level. Okay. Also 2 dash and 4 dash will be at same level. So I have not been able to draw these at same level, but these will be at same level. Okay. So and T2 dash will be equal to T4 dash. Right. So then using the isentropic relations, T2 dash by T1 is equal to RP1 gamma minus 1 by gamma. Okay. Implies T2 dash is equal to T1 RP1 gamma minus 1 by gamma, which is 301 into 2.32 raised to power 1.4 minus 1 divided by 1.4. Now if you take the calculator and solve it, this will come out to be, please work this out, this will come out to be 382.81 Kelvin. Let me know if some calculation is wrong at some point. And then for your compressor, the efficiency has been given. Okay, so efficiency has been given. So from here we will calculate T2 because we want to find out compressor work. And what is compressor work? So if you see compressor work, WC is WC1 plus WC2. But the point is, for both the compressors, the work input will be same. And that will be either H2 minus H1 or H4 minus H3. So the result will be same. 2 Cp T2 minus T1. T1 we have, T2 we need to find out. So all this we are doing just to find out T2. Okay. So from this expression, T2 can be found out because NC we have, T2 dash we just found out, T1 we have, T1 we have, T2 we can find out. So let's see this. So just skip this and 0.82 is equal to T2 dash. Now T2 dash is 382.81. 382.81 minus 301 divided by T2 minus 301. Okay. Then implies T2 minus 301 is equal to 382.81 minus 301 plus 0.82. Okay. So now this can also be written as T2 is equal to plus 301. I hope there is no doubt in it, no problem in it. So if we work this out, so this comes out to be 400.76. Okay. It's Kelvin. Now this can be used to find out your WC. Hence, WC is equal to 2 into Cp T2 minus T1 is equal to 2 into 1.005 400.76 minus 301. This comes out to be 200.51 kilojoule per kg. So this is your compressor work. Question number 4. Then question number 5. What it says. Heat added in the combustion chamber. So Q in we need to find out. Question number 5. Solution. Heat added in combustion chamber. Q in is equal to Cp H5 minus H4. Please see the diagram. H5 minus H4. Now, this is Cp T5 minus T4. What is Cp? 1.005. T5 we have? Yes, it's given 1063. T4 do we have? Let's see. So we just calculated T2. Okay. Also because there is perfect intercooling, it means T4 is equal to T4. T4 is equal to T2. The same way as T1 is equal to T3, T dash equals to T4. This means that T4 and these two will be at same level. So just don't go with the diagram when you are just comparing the levels. But essentially this is the meaning. So T4 is 400.76. So if you solve this now, this will be 665.55 kilojoule per kg. Okay. So this is your heat added in combustion chamber. Then 665.55. Actual temperature at exit of low pressure turbine is. So low pressure turbine, let's see. So this is your low pressure turbine. This is your high pressure turbine. So the question asks you to find out T8. Okay, now you need to find out T8. So let's do this. So first we will find out T6 dash, then T6. From T6 we will have our T8, because in the question it is given that for maximum expansion work. Okay, the maximum expansion work will be there only when your T6 is equal to T8. right? So let's do this. So question number 6. So first, for your high pressure turbine, using the isentropic relations, we'll find out T6 dash. So if we find out T6 dash, it will be 1063 divided by 2.32, 0.4 divided by 1.4. So if you solve this, this will come out to be 835.81 Kelvin. This will come out to be this. Then we need to find out now T6. So efficiency of your turbine is given. So expanding it and then placing the values implies efficiency is 0.82, then find out from here it will come out to be 876.70 Kelvin. Then because maximum expansion work has been given, maximum expansion work condition has been given, and the turbine efficiencies are also equal. In that case, T5 is equal to T7, T6 dash is equal to T8 dash, and T6 is equal to T8. Hence, T8 is equal to 876.70 Kelvin. So this is your question number 6. Then question number 7 is there. So, but before moving ahead, we'll take a short 5 minutes break. After that, we will continue with the session. Okay, so let's continue with the session. Thermal efficiency, the question asks of the plant. Thermal efficiency. So, question number 7, this is, I believe, the thermal efficiency eta is W net by Qn. So, W net is Wt minus Wc. Q in is QCC plus QRH because reheater is also there. So this is the reason why with reheater your thermal efficiency decreases because your denominator is increasing. In addition to your combustion chamber heat that is added in a combustion chamber, in your reheater also heat is added. Okay. So 2 into T5 minus T6. So this is for, I hope this is clear. This is for your turbines. Okay. So for your combustion chamber is this plus this. T7 minus T6 is for your T7 minus T6 is for your reheater. 5 to 4 is combustion chamber. 5 to 6 is your turbine. 4 to 3 is your, or 2 to 1 or 4 to 3 is your compressor. So if you work this out, this will come out to be, so take 2 common in the numerator. 1063 minus 876.70 minus minus 400.76 minus 301. So this is your numerator. Denominator is 1063 minus 400.76 plus 1063 minus 876.70. Now if you solve this, this will come out to be 0.20. So this is the thermal efficiency. Then question number 8 of this group. Back work ratio of the plant is, that is back work ratio is work of compressor by work of turbine. So this is high pressure compressor plus low pressure compressor divided by high pressure turbine plus low pressure turbine. Now, because for both the compressors work input is same, for the both the turbines work output is same. So this way it can be done. So 2 into 400.76 minus 2, so divided by 2 into 1063 minus 876.70. So if you solve this, this will come out like this. This. So this is your solution. Back work ratio. So this was about your first group. Then second group is also there. So quickly read this and then we will solve this. Okay, so we have this question. A gas turbine engine consists of two-stage compressor, perfect intercooling. Air at this is taken, compressed air passed through heat exchanger. So heat exchanger is there. In previous question, we didn't have a heat exchanger. And then combustion chamber is there. Heat exchanger has this effectiveness. The turbine inlet pressure is this and temperature is this. Isentropic efficiency of both the compressors is this, and that of turbine is 87%. That's all this. Okay, let's do this. First, we'll draw the diagram. Exchanger is there, 6 to 7, and then 4 to 8. Then what is given to us? Let's jot that down. Given a compressor inlet pressure is given as 1 bar, temperature is given as 295 Kelvin, pressure ratio has been kept at 5.4, maximum temperature 922 Kelvin, efficiency of compressor 0.94, of turbine, then effectiveness of your heat exchanger is 0.78. Then first question is total work consumed by the compressors. The same way we'll find out T2. From T2 we can get the pressure ratio for single compressor is this. So this is 2.32. For perfect intercooling, what is there? T1 is equal to T3. So this time I have drawn a bit closer to reality, this diagram, how actually it should be. And then T2 dash is equal to T4 dash. T2 is equal to T4, or maybe not. T2 dash is equal to T4 dash. Then using isentropic relation for your first compressor, T1 1 to 2, 2 dash. So T1 by T1 is equal to R T1 gamma minus 1 by gamma implies T2 dash is equal to T1. How much is T1? 295 RPs into 2.32 raised to power 1.4 minus 1 divided by 1.4. So if you solve this will come out to be 375.18 Kelvin T2 dash. Then with the efficiency you can calculate compressor this T2. Okay. Now efficiency is T2 dash minus T1 divided by T2 minus T1 implies 0.80 is equal to 375.18 minus 295 divided by T2 minus 295 implies T2 is equal to this. Now if you solve this will come out to be sorry 0.94. .26 Kelvin. This is your 380.26 Kelvin. All right. Then from here you can calculate the total compressor work. Hence, total compressor work high pressure compressor plus low pressure compressor, because both are same, so H2 minus H1 will work. So that is 2 into T2 minus T1. So this is 2 into 380.26 minus 295. You solve this will be 170.52 kilojoule per kg. So this is your compressor work, both the compressors. Then next question is heat added into the combustion chamber. For heat added, what do we need? We need T5 and then we need T8. Okay. Now to find T8, let's see. So this is 5 to 8 we need to find out, right? So for this, what we need is T8, because if you see question number 10, heat added into combustion chamber. So Q in is equal to H5 minus H8, T5 minus T8. T5 we have, T8 we need to find out. So how we can do that? So if you see the efficiency, effectiveness of heat exchanger, that can be calculated this way: T8 minus T4 divided by T6 minus T4. Okay, so T8 minus T4, T6 minus T4. Maximum heat transfer is in denominator, and this actual heat transfer is in numerator. So this is your heat exchanger. Then 0.78 is equal to T8 minus, now if you see, T4 is equal to T2. Why? Because of perfect intercooling. So T4 we have. Which basically is 380.26 divided by T6 minus 380.26. So this we have. But here we don't have T8, we don't have T6. At last, what we are concerned with T8. But to find T8, we need T6 also. Then we need to calculate T6. So how we can calculate T6? So from turbine, for T6, from turbine, what do we have? The isentropic ratios, gamma minus 1 by gamma, implies 922 by T6 dash is equal to 2.32 raised to power 1.4 minus 1 divided by 1.4. This. Then T6 dash comes out to be how much? 724.9 4 Kelvin. I hope you can work this out. Okay. Now after this, we need to find out, we are concerned with T6. So, you know, efficiency implies T6 is equal to 922 minus 0.87, 922 minus 724.94, right? Implies this is 750.55 Kelvin. So T6 now we have, so we can find out now T8. So let's say this is 1, this is 2. Using T6 into, what do we get? T8 is equal to 0.78 into 750.55, because now we have T6 also, minus 380.26 plus 380.26. So this is your value for T8. And if you solve this, this will come out to be this much. T8. Then using T8 in 1. So Q in is equal to 1.005 into 922 minus 669.08. If you solve this, this will come out to be 254.18 kilojoule per kg. So this is the heat added. So this is your question number 10 answer. Then question number 11, back work ratio. Back work ratio is, I believe back work ratio is denoted by RB, if I'm not wrong, WC by WT. So for both the compressors, T2 minus T1 divided by T5 minus T6. T2 minus T1 is for your first compressor and then multiplied by 2. And T5 minus T6 is for your turbine. In single step, the expansion is taking place. So this is P80.26 minus 295 divided by 922 minus 750.55 that we have calculated from turbine. So this, if you calculate, this will come out to be 0.99. This is quite high back work ratio. Usually back work ratio has to be between 0.4 to 0.6. Okay. But because for the sake of solving the numericals for our practice purposes, the values have been taken. So that is fine as far as the practice is concerned. But in reality, if you see, this is too high back vibration, which is not preferable. Then net shaft work. So net shaft work, if you see, question number 12. So shaft work, which is a net. W for C1. So this is H5 minus H6 minus 2 into H2 minus H1, which is equal to T5 minus T6 minus 2 into T2 minus T1. Then 922 minus 750.55, 2 into 380.26 minus 295. Now, if you work this out, this will come out to be 0.93 kilojoule per kg, which again is very, very less shaft work. So numerically, if you see, practically, if you see, this doesn't make sense. But for the sake of numericals, this is fine. Okay, shaft work. Then thermal efficiency of the cycle. Question number 13. If you see thermal efficiency is W net by QA. So 0.93 divided by QN is 254.1. So if you see, this is this ratio. In percentage, this is 0.36%, which again is very, very poor, pathetic thermal efficiency, which we would not, which we will never prefer in any real case scenario, but for the sake of numericals. This is fine. All right then. So this is it, I believe, about today's session. 13th question it was 0.36%. So I can conclude today's session in that case. So there were three lectures, lecture 10, lecture 11, lecture 12. So the topics were based on your gas turbine attachments. So three attachments we have discussed: heat exchanger, reheater, and then intercooler. Heat exchanger, basically what it does, it improves the thermal efficiency by taking heat from the your exhaust gases and giving it to the working fluid that comes out of compressor. Okay, then is your is your heat reheater, sorry, where you give where you split the expansion of the gas coming out from the combustion chamber, and from this, what you essentially do is you increase the work output, the turbine work for the whole cycle. You increase. So this increases the work ratio or turbine work. And then is your intercooler, where the work input required for compressor decreases. All right. So these three attachments have been discussed in this week's content. And then we saw questions based on these three topics and few numericals. All right. So this is it. This is it about today's session. Sorry. And next session again will be on coming Tuesday. So we are having sessions for this particular course on Tuesdays from 6 to 8 p.m. Right? You all are welcome to join these sessions. Until then, goodbye. Thank you for joining this session.